Hi, my name is Natalie Davis, and I decided to answer question 2 for my last tutorial. This question states, imagine you have a linear piece of DNA that is 14 kilobase pairs long, as I've shown by this line. To make a restriction map, you first cut with EcoRI alone, and then SMAI alone. Finally, doing a double digestion using both these restriction enzymes. These are the following digestion products that are obtained. So when you're just using one of these enzymes, shown here, these are the size of the base pairs that would occur. Then when you use both of these are the size of the fragments. So question A asks, how would you have gone about determining how large each fragment of DNA was if you were doing the experiment alone in a lab? The answer to this question is very simple. Gel electrophoresis. When you run a DNA that has been cut by restriction enzymes through the agarose gel, it separates them up by size. We'll see an example of this later on in the tutorial. Question B then asks, by representing the original DNA as a line, draw the relative position of the SMAI cut site. So when we look at using SMA alone, we can see that it separates it into only 2 fragments, each of 7 base pairs long. So this first part is very easy. Because we know this whole thing is 14 kilobase pairs, we can determine that that SMA cuts directly in the middle of the DNA. That's going to separate these 2 individual pieces into 7 kilobase pairs. Question C asks the same thing, but this time only using EcoRI alone. So when you're only using one restriction enzyme, you can't actually tell the exact position until you do the double digestion. So this is just an approximation of where they would be. Generally speaking, that enzyme could have cut here to make this 3 base pairs. It could have cut here, making this 5, and then this last piece would be 6. Now that we can do a double digestion, we can determine the exact location of these cut sites. The easiest way to go about this is to start with the enzyme that separates it into the least amount of pieces. For this question, that's going to be the SMAI. So let's put that on the map first. Because we know this whole thing is 14 and these are each going to be 7, we can determine that's going to be exactly in the middle. Each of these large pieces is now 7. The next easiest step would be to look at the base pairs that result after the double digestion. We should determine which 2 of these would add up to 7. So that's going to be 3 and 4 equal 7, and 2 and 5 equal 7. Now let's look at using ECO. We can see that a fragment of 3 results when we're using only this enzyme, and a fragment of 3 results when we're using both. So let's put that first one right here in the beginning. To then equal 7, this next piece is automatically going to be 4. This next piece is also 7, so to break that up, it's going to be 5 and 2. We know that one of the fragments of using ECO needs to be 6. 4 and 2 equals 6, so let's take this 4, let's use ECO and cut here, and now this whole fragment in between these 2 is now 6. That leaves us with this last piece. If this is 2, that's leaving us with the last piece being 5. So we have all of the base pairs that result from ECO, i.e. 3, 5, and this whole thing being 6 if that cut was not there. We have 7 and 7 if it was just SMA. And now we have all of the double digestion base pairs. Those are 2, 3, 4, and 5. Question E asks, imagine you have a gene, M+, that contains the SMA I site. When this site is mutated, M-, SMA can no longer cut, and the mutation causes an albino phenotype in the homozygous M-, M-, i.e. this is a recessive condition. We're going to draw out the electrophoresis gel image that shows the restriction fragments for a double digest containing all wild type and all albino conditions. So as stated before, this is a recessive mutation. So when we have the heterozygous pairing, that's going to result in a wild type or normal gel electrophoresis. So starting with the wild type, that wild type is going to be as if both of those restriction enzymes cut, like we just saw. So that's going to result in base pairs of 2, 3, 4, and 5. Now, M-, M- means that the SMA-I did not cut, and therefore it's just like as if only ECO cut. So that's going to be like that first problem, where it's only one restriction enzyme, resulting in 6, 5, and 3. So because this is a recessive mutation, this one is going to be exactly like the first one. The SMA still cuts, it only fails to cut in the middle one. As long as that wild type is present, the SMA will still cut. Finally, F is my what if question. My what if is, what if we wanted to stitch back together two DNAs that had been cut by the ECO RI? So let's say we have this fragment of DNA. We know that the ECO cuts here and here. So if you separated those up, this is what the resulting cut DNA would look like. Now, if we wanted to stitch those back together, we could, because these are cohesive or sticky ends, i.e. they're not blunt ends, and if we had two different DNAs, those could be stitched back together. So let's say we have this DNA, and this DNA. If we wanted to stick those back together, it would look like this. We would have the G from one, and then the resulting from the other. And likewise, we would have this blue end, and then this one from the red. It's exactly the same as what we started with, but we have actually two different DNAs that have been put together. DNA ligase would then come in and seal up those gaps. And that concludes my tutorial.